Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. As always, we have a great webinar on tap, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will be able to listen to the webcast on demand. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time you have a question for our speaker, please don't wait, don't hesitate. Just use your GoToWebinar control panel and submit your questions. And we'll take as many as we can near the end of today's webinar. And finally, today at the end of the webinar, we will be doing a drawing for 3 $50 Amazon gift cards. So stick around. Hopefully your name will be one of the 3 lucky winners. Okay, with that, we'll go ahead and kick off today's webinar, which is how to find malicious backdoors and business logic vulnerabilities in your code. Our speaker today is Chetan Kaneki, who is founder and CTO of Shift Left. Hi, Chetan, how are you?
I'm doing great, Charlene. Thank you very much.
Good. Well, I'm going to put myself on mute and let you get right into your presentation.
Excellent. So very good morning, good evening, and good night to all the attendees listening on this webinar. My name is Chetan Kaneki. I'm the founder and CTO of Shift Left. So let me start this presentation with explaining what we do at Shift Left. Every company is writing software, and much of it today is deployed in the cloud. In this world, attackers both from inside and outside are leveraging these applications as conduit to all important data that actually represents your customers that you're servicing. The unit of value is thus code, source code, because every application emerges at source code, and this source code is packaged and then deployed into this cloud to serve your customers. Shift Left has the best understanding of code and its modern interpretation to help developers identify what needs to be fixed, hence the name Shift Left. In today's webinar, we will discuss the following topics. As we alluded to, we'll talk of source code, which essentially is the unit of your value. And what are the common traits of source code? Because all of us as engineers write source code in several programming languages. And eventually the source code is, as mentioned, compiled and packaged and deployed to production. Then we're going to emphasize on what is code property graph, the key foundational technology of Shift Left, and its applicability to your unit of value, which is source code. And then we're going to speak of backdoors, or perhaps insider threats, and how we're going to leverage a product called as Ocula, built on the foundational technology of code property graph, to help hunt for backdoors and insider threat patterns. Given that we mentioned source code, and source code is essentially written in several programming languages, there is essentially a common trait amongst all these programming languages, which essentially represent source code. And those common traits are a minimum sequence of characters, because source code eventually is almost akin to spoken language, and each spoken language actually has a grammar. Likewise, as we utilize programming languages, as we write programs, they're measured against a certain grammar that defines the programming language. So the grammar essentially has a minimum sequence of characters that represents the alphabets of the programming language. In adherence to the programming language, grammar tokens can be combined to represent a single statement. And what you see on the far left in the section where I mentioned lexing, statements can be assignments, branches, control, and conditional evaluation types. Now, as we write multiple statements and sequences, they can be combined together to create a basic block. And that basic block essentially represents a function. So what you see on the right-hand side and the middle, in quotes of parsing and IR, is nothing but a function representing a series of statements to serve a certain business need. Now, as we write multiple functions, they essentially connect together and pass data in lieu of communicating to create a data flow. And this data flow is nothing in business parlance, workflow. If we are conducting a banking transaction, we obviously have to validate the funds in the source account, destination account, and then trigger the transfer. So think of all of these encapsulated in a series of functions that are connected together to serve that business need. Software systems, as we write them, have varying degrees of complexity because they're composed of many interacting elements. A natural way to abstract over these complex relationships is to model the application. The application essentially comprising of the code that you write, the open source dependencies that it utilizes, and the framework that it is deployed upon as one single connected graph. Because as we mentioned, we are using functions that we write, and perhaps functions that we are using from the open source library and the framework. So in a sense, all these functions as they communicate together represent a very dense connected graph. Being an evolving system, this very dense applications graph evolves along time, mostly by growing. Because as we put new releases out, we are adding new features. As these libraries are increasing in version scope, new functionality is added. So likewise, as all of these changes are occurring, the graph is becoming more dense. Owing to this, it becomes relatively hard to assess and comprehend the security posture of the application in totality. Because as engineers, we're writing code very fast to deploy new features in the product. And perhaps we might land up misusing an open source library in a certain way. And the consequence of all of this is common vulnerabilities introduced in the application, or perhaps business logic flaws. And then the other category that we're going to touch on in detail, which is what we call as insider attacks, where individuals intentionally place certain patterns in the code to serve their needs from a malicious intent. So upon grokking at this complex composition, can we answer the following questions? Is the application compliant in treating sensitive data with care? Because all our customer data is sensitive. Can authentication logic that we use to essentially differentiate between customer A and B be bypassed by any attacker in this complex composition? The other question is this code using an open source library in an unsafe way? And finally, is the application at risk to insider attacks? Very hard questions, but fear not, as the all-encompassing code property graph, which is the foundational technology of shift left, is here to your rescue. The CPG is essentially a versatile graph of graphs, depicting connectivity of the application's fabric and all of its piece parts. As we mentioned, the piece parts are code that you write, open source that you consume, and the framework that you're deployed upon. This CPG creates a multi-layered, three-dimensional representation of the code's call graph, which represents data flow, configuration, etc., which provides unprecedented insights to the developers and analysts to fundamentally understand the application security posture through its evolution. CPG details include representation of the raw programming language, custom code, open source elements, and how all of these interact together by virtue of a very powerful data structure. High-level information flows are the second core ingredient of CPG. This notion of high-level information flow is inspired from Unix file descriptors. That is the idea to mark parameters of sources, identify all sensitive sinks in your application, because your application is obviously communicating with either a database, file system, other microservices over the socket, and reading from and writing to memory units. So on the basis of modeling your entire application with the notion of sources, sinks, and transformers, it becomes relatively easier to understand high-level information flow from the point of inception to the point of trigger. Now let's double-click into the core discussion of this webinar, which is insider threats. One of the most dangerous threats to an organization comes from the inside, from a group of people known as trusted insiders, comprising of employees, former employees, contractors, and perhaps technology partners. Note, as all these relationships are established, meaning as you onboard an employee, or as you offboard an employee, or perhaps onboard a partner, all of these folks have access to your critical properties, like source code, credentials to your data center, again, depending on their function associated with the partnership. Operating alone or as a member of an organized crime unit, trusted insiders are individuals who have privileged access to sensitive data and infrastructure in the organization. So they have the privilege to essentially abuse these rights that have been provided to them. So what I have on screen here is a quote from CERT's recent study on insider threat issue. And the study is fairly interesting because the population on the study was 49 case units, out of which 86% of the insiders had technical positions in the organization. 90% of them were granted system privileges, both in the perspective of access to source code or perhaps infrastructure or authorization or authentication units. In those cases, 81% of the organizations that were attacked experienced a negative financial impact as a result of insider activities. And the losses ranged from low to $500 to highs of tens to millions of dollars. So this is a serious problem that we should take into consideration. But the question is, how can we solve for this problem? Because to further highlight the insidiousness of insider threat, let's say an insider plans to manipulate the logic of authentication that you're actually using in your applications company-wide. If they manipulate it, it enables him or her to spoof identities and act as a user of the application, perhaps creating an authentication backdoor. And this can be seeded by this individual manipulating your source code, which we'll see shortly, where they plant an Easter egg or a magic value that enables them to trigger this bypass. So let's double click and understand what attackers can do with backdoors. This is just a small list, but the list is endless. Firstly, they can install a backdoor for future access to the system, meaning through the application, they can plant a shell code and laterally move to your host and from your host to your network and take control of your entire zone. They can destroy sensitive data stored on the database while riding on that established connection from the application to the database. Of course, you're going to set a user of type application with certain privileges, and your application can read from and write to the database. So someone having control of your application essentially can interact with the database using the application's credentials. They can log sensitive information generated by the application intentionally, such as credit card numbers, passwords, encryption keys, and so forth, because as you log, that data is being persisted to your disk, and then you have a certain log rotation logic that aggregates that information using an RSys log daemon, and then pushes it to your log aggregation vendor like Splunk or Sumo Logic. Now, these vendors might do a good job at hiding sensitive data, but insiders can effectively log to your file system, and before it reaches those aggregators, pick that data and use it in a malicious way. And lastly, they can execute OS commands using user's identity or application's identity and provide a remote command prompt using a reverse shell. Now, these are all the use cases, but the use cases are limitless. So let's shift gears and understand how you can identify these threat patterns or insider threat patterns or perhaps backdoors in your code using shift-left Ocular. Shift-left Ocular is an interactive query engine over this foundational code property graph that we spoke of. And just to regurgitate, code property graph is a graph of graphs connecting your application's custom code to your open source to the framework. And this Ocular tool enables your advanced security teams and developers to essentially take security requirements, construct what we call a security as code, and interactively inquire to identify if your source code contains such patterns that would lead to backdoors. Now let us demonstrate the ability of Ocular using an example open source code base called as tarpit. The GitHub moniker to that code base is available, so you can play with it as you get your Ocular trial going. So let us switch gears and jump into the console to illustrate how we're going to use Ocular to identify threat patterns. So the first step is I have checked out or cloned this repository called as tarpit. Tarpit can be compiled either using Maven or Gradle. So I'm going to build this package using Maven. Given that tarpit is a Java project, the consequence of building this project creates a WAR file. The WAR file or a jar file is a compressed archive or a package representing your application that can be deployed. So as this jar is created, we are going to use Ocular in interaction mode to traverse your code and identify the existence of such patterns. Ocular is a simple command line distribution that can be installed in your controlled infrastructure. And the code base can be loaded into this interactive session to thereafter ask questions associated with your application to identify insider threats. So the first step that I'm going to do is create this code property graph that we just spoke of. The command for that is create CPG and SP. And notice I have specified the absolute path of the WAR file. So this step takes the WAR file as an input in this interactive session and goes ahead and creates the graph and loads it into this active session for interaction. Ocula has this concept of workspaces. You can load one or more jar, WAR files, or any artifact into this workspace and selectively switch context between each one of them. So the first step is we're going to load the graph that we just created not too long ago. So upon loading this graph into the session, we can begin to ask very interesting questions associated with the graph. The first question is, give me all dependencies associated with the application. Note, it returns version dependent pairs of all open source dependencies utilized by the application. The next step that I'm going to do is import some convenience functions. By the way, we'll see it shortly, but you can create very many convenience functions in order to take repeatable value and incorporate that into a function so that your other investigators, your developers can reuse these units. Now, like we spoke of, code property graph takes your entire application construct and models it by virtue of this source, sink, and transformer paradigm. So just to give you a sense of what this paradigm comprises of, we're going to ask the CPG that we just loaded, give me all sinks that exist in the application. And again, to define sinks, these are external resources that your application is communicating with, either from perspective of read or write. I executed a simple command. The command is cpg.sync.method.fullname distinct. Now, these are all sensitive sinks that are pre-annotated by shift left API for you, so that you have a very clear understanding of all external communication by your application. We call this sensitive because any communication is either by virtue of read from or write to. And when you're dealing with your customer data, you're either doing one of these functions. So just to quickly illustrate, we see runtime.exec used here. We see a prepare statement, which implies that you're writing or reading from database. And then there's several file system APIs or packages that are loaded, which implies that you're interacting with the file system as well. So let us now ask an interesting question of, given that this is a web application, give me all the sources in the web application, which is, of course, given it's a web application, you have an endpoint listening on the socket. And perhaps if you're using a web framework, you use an HTTP API to accept either GET or POST requests. So again, we use a very simple API, which is cpg.method.parameter eval type. And let me explain this. This is saying, give me all methods that accept a parameter of type HTTP, which could essentially be HTTP request, HTTP servlet request, or if you're using higher level frameworks like Spring, they provide convenience functions which effectively abstract over these base HTTP requests. So out here, I'm getting all the methods that accept parameter HTTP request, and I'm filtering by packages of type shift left. Because if I don't apply the filter, it's going to return the entire open source representation of all packages as well. So clearly indicates here that we got several post and get requests that we're using in this web app. So let us switch gears and look at all the types that we're using in this source code. Again, simple API cpg.type decal.fullname. Of course, as we write code, we use types. These types could be user-defined types like, class bank account, class customer, or you might use a primitive type like java.lang.string, .boolean, .integer. So CPG lets you quickly ask whether you're using a certain type in your code. And this is very interesting even to glance at, because it'll give you a clue of whether a certain type which is suspicious is used in the code. Like, for example, if you're using java.lang.classLoader, this is a suspicious type because class loader is all about letting dynamic loading of classes. And if anyone is using that in the code, for either an intentional good purpose or a malicious purpose, you need to double click into it. Now let us ask another interesting question. We looked at types. Let's switch gear and look at all literals or constants defined in your code. Literals are nothing but strings that you've hard-coded in your application. Now, if you're dealing with tens and millions of lines of code, imagine if you were code reviewing, it would take a long time for you to identify whether anyone has hard-coded something that is a bad code practice, or perhaps it carries some degree of a suspicious trait. And if you were to code review this, it takes an absurdly long time. So by virtue of simple API, which is cpg.method.literal.code, you get a list of all hard-coded literals in your code. Again, merely taking a quick glance at it gives you very interesting insights. First of all, if it's not UTF-8 compliant, you might see log messages in these literals. In certain cases, you might see hard-coded database credentials, or perhaps AWS keys at times, which we'll double click into shortly. So now I'm going to take that same API and ask a question of saying, in these literals, can you filter and let me know if there's any AWS secret or cloud credentials hard-coded? Lo and behold, there is. So now I want to double click further because I want to essentially mark this code review as failed. I'd like to ask which method is encompassing this hard coding of this literal. So I take the same API, which is cpg.method.literal.code. I filter by AWS secret, and note that shift left provides you a dictionary of all secret types, access token types associated with every cloud vendor. So you don't have to do that work. Now we get the method in which this particular hard coding has occurred, which is io.shiftleft.tarpit do get. So let's quickly switch it to this code and see where exactly this is hard coded. I'm going to switch here, go to servlet tarpit do get, servlet tarpit.java do get, and there you go. The credentials are hard coded. Bad code practice, and if this is committed to your open source repository or perhaps your closed source repository, you carry the danger of your credentials being leaked, if not rotated, or if rotated in its due course of time. So using the same API, we can ask questions of whether you have hard-coded database credentials as well. So we merely scratched the surface here. The sky is not the limit with Ocular's interactive API. So let us use this API to uncover information flows with symptoms leading to insider attacks. And for that, let's quickly switch to the presentation again. The first case that we're going to speak of is what we call as a logic bomb. Logic bomb is fairly interesting because they are known cases, known documented cases of logic bomb. What is a logic bomb? A logic bomb is a piece of malicious code that is executed when a specific trigger condition is met. A typical example would be a program that monitors company's payroll system and attacks the company if a specific employee is terminated. So a time bomb, because logic bombs have different variants, as we spoke of, it is triggered. It could be triggered by time. So a time bomb is a type of a logic bomb that uses a date and time as a trigger function. So when a date or a time bomb or logic bomb is detonated, it may perform a denial of service, such as crashing your system, deleting critical data, or degrading your overall response time of your entire application. So let us examine this code snippet, which is a part of that open source project that we spoke of, which carries the symptoms or exhibits the symptoms of a logic bomb. So I've extracted two portions of the code just to draw attention. The first section where I'm hovering my mouse is you see a string command, which essentially contains an encoded literal. And this encoded string is passed to a function called as ticking. And if you quickly glance at ticking, it is acquiring an instance of calendar type and then decoding this literal and executing that literal if a certain condition is met. Now, this is a very simple representation, but if someone with malicious intent had to plant this, they would go to length to place this literal in some other file in a very large code corpus and make this code function relatively complex so that it escapes a typical code review. And note that there is a spectrum of efficacy in the process of code review in organizations. When you're dealing with legacy code, which is tens and millions of lines with accrued technical debt, it's relatively hard to understand what is being introduced and stay on top of your code reviews. So let us switch into the Ocular prompt and see if we can traverse and navigate this case and identify for this existence of the symptom. The first question that we're going to ask is, sinks. We saw this earlier not too long ago. Give me all sinks that exist in this code. we saw there were a laundry list of sinks, some interacting with the database, some archiving, some unarchiving certain compressed payloads. But specifically, we saw this pattern decode. Decode means we are essentially decoding something that has been encoded. And what we saw in the presentation was this hard-coded literal, which had a pattern that represented an encoded string. So here I'm filtering down, I'm calling cpg.sync.method filter containing a pattern decode. And lo and behold, I get a list with two elements. One is a base64 decoder of type java.util, and the other is sun.miscellaneous base64 decoder. So it implies that this program that we're speaking of is using a decode function of these types. So let's double click and see where it is used, because we want to get down to it and figure out where is this decode function happening. And lo and behold, it's at this function called as ticking, which we just saw in this presentation. And there's several other functions used, but our topic of discussion is going to focus on ticking. Now we know that decode is being used in a function called ticking, and it is using base64 decoding. So let's use a convenience function of shift left to identify what is being decoded. So we effectively have to take this complex string that we just saw and apply a decode function to see what is actually being decoded and executed. For this, we're going to use an API called as getSuspiciousLiterals. So this API is going to link through all literals and identify patterns which represent encoded, or albeit base64 or any other type of encoding, and decode that using base64. So we see two types here, but specifically what we saw in the presentation was this type. And we received a value which almost indicates that there is a shell script that has been provisioned on this host. It could be provisioned anywhere as a part of your code as well, but it's kind of suspicious that we have a literal representing a shell script which is being executed at a certain interval. Now, let's identify which method which is actually encompassing this, which we already saw. So getTicking held that literal, but there is another super method which is exposed called as doGet on your HTTP route that is encompassing this ticking function. So note that as we defined a logic time bomb or a logic bomb per se, it is always triggered based on a certain condition. The condition could be time, or the condition could be request, or anything else. In this case, it's evident that we have doGet, which is typically initiated every time your customers interact with your application. And that in turn is calling ticking, and that is comparing for a date function, and then triggering the execution of this function or this particular shell script. So what we're going to do is we're going to use the source sync transformation paradigm, because that is the higher level information flow provided by shift left that lets you identify patterns that exist in your code. So the first thing that we're going to do is take this cpg.literal.code that contains this pattern and assign it to a variable source. The next thing that we're going to do is identify if this source is connected to a sink. That sink is a decode function. So over here, we are saying cpg.method.name decode, meaning if you see a method which is called decode that has a parameter of eval type string, because if we quickly switch back to the presentation, we have decode, which is called on a parameter of type string, and that string is accepting an encoded function. So here we're saying, give me all sinks of type decode that accepts a parameter of type string. Now we're going to conduct what we call as high-level flow analysis. Over here, we're going to connect the source and the sink together to illustrate how this information flows. So as a result, what you get is almost a Google Maps-like view of how information is traversing from the source to the sink. So here it is evident that a particular literal is tracked at doGet via a function called a sticking, which is encompassing the decode function. So now we have proof that hard-coded literal is being decoded. But now what? We have to further identify to see if we have time functions in the code which are being compared to enable the triggering of this time bomb or logic bomb. So again, I'm using patterns here in this, here I'm asking cpg.method.full name calendar, meaning are we using any calendar function in this application? Given that I'm using raw APIs, I'm intentionally showing you these patterns because that exemplifies the power of Ocular, meaning that you can use patterns to hunt for the existence of flows associated with threats. But what we have done as shift left is encapsulated these patterns into high-level constructs, so you don't have to do it. You can just say calendar function, and behind calendar we have encapsulated calendar dot, time dot, Joda time dot, etc. So it makes it easier for you to conduct your investigation. So it's evident that again in ticking we're using calendar.set, and now we're going to mark this as source to see if in ticking we are doing some degree of comparison between calendar.set and after. So this would give us a sense of whether we have a control loop within that code which is accepting this hard-coded encoded literal and checking for a condition and then executing that time bomb or shell script per se. So here it's evident that we have a calendar function as well. So these two symptoms are bearing down and telling us that this piece of code is definitely suspicious. So finally, we're going to ask the last question. Is there a connection between that literal, that hard-coded literal that we have, again asking the same API, which is cpg.literal.code, to an command injection function? That could be prepare query runtime.get runtime, java.process builder, etc. Anything that enables execution of a remote command. So this here we're marking the sink as globals.command injection sink. Like I mentioned to you, we have done the grunt work of encapsulating all the types of remote command injection patterns that can exist in your code. So you don't have to do that using patterns like we earlier saw. So here we have the source and sink paradigm. Again, we're going to pull out the flows, and here you see the entire pattern and the trace, which implies that we have all these three conditions that clearly tell you that something bad is going on, and that bad is associated with a logic bomb. So now we have a convenience function that takes this entire flow and gives you a JSONified representation. Great. So that you can export it to your SIM, SOAR, or any other system that you want to draw decisions with. So again, the power of Ocula is not just restricted to investigation. You can directly create an issue in GitHub, taking all this data, this flow string that we created with description, so you can influence your code review process. So using a convenience command, create issues in GitHub. I quickly took that data and I pushed it to GitHub. So if you traverse to issues where we saw 0 issues now, and I get here, there is 1 issue that has been created. So Ocula is just not restricted to GitHub. You can create your own SaaS interactions with other convenience tools that you use in your ecosystem. Now, we conducted investigation. The next affirmative step is you encapsulate this entire investigation into a script and then append it to your CI/CD pipeline, so you measure for it release per release. So let's look at how this can be done. We saw that Ocula can be utilized in interaction mode because that's the first step. You ask questions. Now you take that questions, encapsulate it into an automata, and execute it release per release. So this command can be attached or deployed into your build systems or any other system in your pipeline, which says execute Ocular, pass the script, which we have I've taken this entire investigation, put it in a script, and pass as input the jar file and get an output. So this is executing the script by loading the environment and then piping the results into out.log. And note that if I go to out.log, I have the entire result set with the clear explanation of what is happening, which is, there is a name of function calls, list of suspicious encoded literals, name of suspicious literal initialized within the scope of the function, and the entire call trace. So again, these scripts can be created by you, and we have created premium packages for business logic flaws and insider threats that you can leverage and utilize in your organization. So in summary, what we're seeing here is investigating for a logic bomb, identifying all the patterns behind leading for its execution, and then creating an issue automatically through Ocula in scope of session into GitHub, and then encapsulating all of this into a script and executing or appending it into your CI/CD pipeline. So let's switch and look at another use case, which is called as magic value or Easter egg, perhaps. This is a very, very common pattern. I've lived through it in the past when I was an engineer myself. Most of the time, when we are dealing with critical data of our customers, every organization applies necessary gates and measures and audits to ensure that individuals touching sensitive data is captured in a system of record. And this is a compliance need, and no one can escape this. So often engineers, both intentionally and maliciously, create what they call as Easter eggs or perhaps magic values. Now, if you have a certain form in your application, what an engineer could do is seed and hard-coded value into a certain field in the form. And using that hard-coded value, what they could do is either a redirect to another page, which directly exposes the database console, so that if assume that they're debugging a really complex issue, rather than going through gates of compliance, what they can do is effectively bypass those gates and directly touch the console and query the database to get what they need. Someone could do it with good intention, but if this is seeded, both either good or bad, it could be abused in different ways. So let us try to examine and investigate for such patterns that exist in your code. Again, switching into Ocular, we're going to ask a set of questions. The first question that we're going to ask is, do you have an HTTP source? It's evident that we do have HTTP sources because we saw that earlier. We're using the simple API that says cpg.method.eval type HTTP sources. So the next question that we're going to ask is command injection sinks. And what we saw in this presentation, it was clearly evident that we have a request that is emerging from the source, is fetching a parameter of type trace function, and then evaluating a control flow to see if the trace function is holding a literal of type magic value or Easter egg, and then executing a command injection type function, which is runtime.getRuntime, or perhaps a redirection to a certain console page, etc. So marking source and sink, we're going to check for a condition in between. This is another interesting part of Ocula, where we are saying if there is communication between source and sink, is there a condition in between? And that condition could be equals, greater than, less than, and equals often has an argument set. And here we're saying filter on argument set with order 1, because we are only comparing this Easter egg to certain value, and then executing this command. So now we're going to expand this source sink flow to bring in a new construct, which is what we call as branch point reachable by. This is fairly interesting here, because we're saying, can a source touch a sink with a branch point or a control flow? That could be an if condition or any other construct that is evaluating for a certain condition between the source and sink. So using this construct, we get the flow again, because always the results are represented like a map that gives you a very detailed trace of the entire flow. And it's evident here that we have a parameter that's fetched from the HTTP request that eventually touches runtime.getRuntimeExecute. So this lets you identify if you have hard-coded comparisons in your control flow, which is almost a degree 1 of suspicion before you proceed to check whether you have some degree of an Easter egg like insider threat in your application. So let's now switch to insider attacks, which is sensitive data leaked to file. This is a very common pattern, mostly by virtue of mistakes that engineers commit, and in certain cases intentionally placed by malicious insiders. So all of us use loggers, and often we log information as either info, debug, or trace, or warn perhaps. Now, if you notice, we have 2 statements here, which is user, and we are logging out the user object saying successfully logged in. We want to do it with all good intentions. But a malicious insider can effectively do this with bad intentions as well, because the first step, like we discussed earlier, is to write out sensitive data, which representing your users, to a log file on your disk, and exfiltrate that log file before it is aggregated and shipped off using rsyslog to your log aggregation vendor. So it's sorts of 2 steps, but let's explore if step 1 exists, where if someone is logging sensitive data on a channel that is not supposed to essentially hold sensitive data in clear text. So let's investigate for step 1. So Ocula provides you a very, very interesting construct using an underlying technology powered by natural language processing. Using Ocula, you can identify all things sensitive in your code. By meaning all things sensitive, as engineers, we use variables. We name variables in a certain way, and we often use good naming convention because we want to. It's a good code practice. So by virtue of naming conventions, Ocular and the foundational CPG uses natural language processing and machine learning to classify such elements as sensitive. And these names are matched against various terms derived from compliance bodies like GDPR, SOC 1, Type 1, Type 2, HIPAA, PII, etc. So let's further filter on this list to identify all user-defined types, because there are typically 2 types. One is system-defined types like java.lang.string. You might call something as var AWS keys is equal to something. Or perhaps you might define a class user and instantiate that class user. So in this case, we'll focus on identifying user-defined types because they hold more interesting data, which has high degree of sensitivity. So in this case, we are saying, give me sensitive type, a filter by shift left package, and we've got 2, which is model user and model order. So if we switch context quickly to code to see why this matched up, let's traverse to the shift left tarpit and look at model. Model is encompassing a class, particular type user, and user contains various attributes like username, first name, last name, passport number, address, zip code, etc. So it's evident that you have type location, sensitive PII, first name, last name, zip code. So using natural language processing, we score this entire unit, and then by virtue of identifying, matching up against these dictionaries, we quantify it as sensitive. So now, given that we have something sensitive, we want to identify whether instances of such sensitive elements are created. So for this, we are saying cpg.local.eval type of type user. We're using an example here. Give me the referencing identifiers, meaning is it being used in the application? The next, again, we're using the same source sync paradigm. We're saying initialize a sync of type cpg.method associated with loggers. Now we're conducting flow analysis like we have done in the past. And we're saying, give me all the flows that accepts or creates an instance or references an instance of type user but eventually lands up in a log file. And now you've got a long trace, and not just one, but several. That indicates that you have these attributes of the user object type that is being directly piped or logged onto using the logging function. More interesting is what is happening in between, because eventually, as good practices, what we can often do is encrypt, obfuscate, or perhaps redact certain sensitive elements before we log them out. So it's clear that in between, nothing of this sort is happening, which clearly indicates that this is bad practice and something suspicious could be going on, either intentionally or by mistake. So we can ask the same question by using a construct called as pass-is-not. And here we have encapsulated different types of redaction encryption functions by using classified tags as obfuscate, redact, and encrypt. So using this, we can say pass-is-not means it is not passing, or you say passes, and passes essentially can return nothing or something, depending on whether you're using such function. So it's evident that this engineer is not obfuscating and redacting because the results are none. So let us now switch context quickly and look at another use case, which is the next use case, meaning this malicious user logged sensitive elements, and he has created a backdoor in the application to exfiltrate that data. And for this, there could be a REST API endpoint that accepts, or it could be get or post, accepts a parameter. It could be a path to that file, and this particular file is inspected or inspected on the file system. Contents are read and fed back to the response, which is essentially sent back to the browser. So this is a trivial amount of code. Note that it could be as simple as this or hidden from naked eye with varying degrees of complexity. So let's quickly traverse or use shift left Ocular to identify this pattern. It's again very simple. We're asking for HTTP endpoints. We are looking for all path traversal sinks. In this case, we have a file system access, which is why it's quantified or classified as path traversal. Again, we look up flows, and it's evident that we have several flows that emerge at the source, is conducting some degrees of functions and touching the file system. All of these investigations can be encapsulated as recipes and then executed to effectively influence your build or fail a certain code review or virtue of comments, etc., like we had indicated earlier. So let's lastly look at a very interesting case. This is again what we call as attacker using compiler API. This is again a very common trait and pattern. There are various use cases and real use cases of this attack, which was materialized. Typically, DevOps bakes, if you're speaking JDKs and JVMs, for simplicity, DevOps typically bakes images of the JDK, typically not hardened, into your Docker containers or your physical appliance, or perhaps your virtual appliances, upon which your applications are deployed. Now, when a JDK is deployed, it makes the Java compiler API available to compile an attack class. And note this attack class can either be passed by an attacker-controlled input through an HTTP source, or again, like you saw earlier, it can be encoded, hard-coded as a literal, placed somewhere hidden in a globals file that is called upon by your source code. So let's carefully examine these two constructs in screenshots here. You see a string source, a long obfuscated or encoded string, which actually represents this particular string, which is a class, which contains a static type and a constructor. And notice that there are a series of function blocks here. The first thing it's doing is decoding this encoded string, saving this as a .java file in some restricted folder or any folder on your file system, and then in initializing an instance of the compiler, because now you have the JDK available at your dispense. So now you can compile this attack class. So this particular call is compiling the attack class and then instantiating the attack class or loading it in the final construct. Now this piece of code seems very innocuous, and for the most part, it escapes any code review. But it contains a malicious intent that has all patterns of an insider attack. So let's quickly shift gears and look at how we can identify this using Ocular. Again, let's bring up that same API that we brought on earlier, which is globals.getSuspiciousLiterals. And notice that we got two. In the first use case, we looked at that evil script that was executed through the time bomb. And here we have this very long literal that is representing this particular decoded package. Now, when you see something like this, it is suspicious, spot on, because why is someone encapsulating Java code as an encoded literal in your code base? So let's go ahead and again mark this as a source, this entire encoded literal, and file sync, because the first thing we saw is a particular class a particular file of .java type is being created on the file system, and this particular decoded representation of this encoded literal is saved or persisted. So here with Reachability API, you're able to move from this literal directly to the file system write command. So it's evident that we have the first suspicious pattern. The next is we're going to ask the question of if any compiler type construct is used. And obviously JDK enable javax.tools.compiler is being used in the code. And this inquiry is by virtue of cpg.type Decode. Give me all the types that are used in the code. So again, we're going to take this particular type, which is a file sync, mark it as a source, and then we're going to inquire for the full name of the compiler sync that we spoke of to identify reachability. So in this case, again, we got a flow which is suspicious element 2. And then we're going to ask the final question, which is, if this class is saved, now is it being compiled and instantiated? So this is suspicious element 3. So note that these 3 patterns existed sorts of in unison, but they separately existed. And using Ocular, you can separately inquire them and eventually bind them together to see if all these 3 conditions had flows in them, and then create this intrinsic connection. So by virtue of creating this connection, you've effectively concluded that you have this pattern that exists in the code. Similarly, this was a hard code that was placed by an insider with malicious intent. Likewise, that individual can influence or send any class through an HTTP request. So this is another pattern where you fetch the parameter and directly decode the buffer and instantiate the class. And most of the time, if you're encoding the element, it bypasses your standard application firewalls. And often pattern matching on base 64 encoded elements is not good enough. And this is another quick pattern, lastly, which is called as escape validation, which is fairly interesting. If your organization has created a standard validation framework and a malicious user wants to bypass, because you have mandated every application should use this validation framework, that individual could encode this particular string, pass it through the validation function, because obviously the validation function is checking for patterns. It's not going to identify anything in the encoded string and return the original string. So in this case, the original string is returned, it enters the loop, which is the branch condition, and then the decode function happens and the query is executed, or the malicious query is executed. So finally, the core essence of to summarize what we accomplish using Ocula is it enables development security teams to create AppSec requirements for our scripts, which is essentially security as code. And using these scripts, you can enforce execution in CI/CD pipelines to conduct checks for security posture of every release. And then You can create your own scripts or use or leverage shift left packages, specifically software composition analysis, business logic flaws, sensitive data leaks, and insider attack patterns to identify and stop any builds from proceeding to be deployed in production. Thank you for listening, and I would encourage all of you to try Ocula on your code. We have a 14-day free Ocula trial. The trial version does not include security profile queries and policies and some convenience functions that we spoke of. But if you want to participate in the proof of concept, please email sales@shiftleft.io. We support Java, .NET, C, and C++, and you can utilize a proof of concept with a full-featured Ocula version with support and training. Thank you very much. Hope you enjoyed the training.
Great, thank you, Chetan. We are unfortunately past the ending point, so we're not going to be able to take any questions. And I know I did promise the drawing for the 3 Amazon gift cards. We will be notifying the winners via email since we are past time, but I do want to thank the audience for joining us today. Chetan, thank you very much for a great presentation. We appreciate it very much.
Thank you, appreciate it.
Great. All right, this is Charlene O'Hanlon, and I'm signing off. Have a great day, everybody.